Dear students, I have come with a new module, Computation of Karl Pearson's Coefficient of Correlation, taking deviations from actual mean. There are two methods for computation. One is taking deviations from actual mean and one is from assumed mean. So in this module, we are going to explain how we will compute Karl Pearson's Coefficient of Correlation, taking deviations from actual mean. So there are three assumptions for computing Karl Pearson's coefficient of correlation. This is important because based on these assumptions, they have framed the computation. So first one is normality. That one is the correlated variables are affected by a number of independent factors so that they acquire normality. Normal distribution, that is important for statistical computation. Say for example, if you take the expenditure pattern of a household, there are so many factors affecting that. That is number of members in the family, whether it's a vegetarian family or non-vegetarian family, the age of the members, whether both the parents are working, number of children, household expenses, so many things are related. So any variable if you study, there are number of factors affecting that result. Second one is causal relationship. There is a causal relationship between the variables. Any item if you study, there is causal relationship between the variables. Income and expenditure, income and tax rate, income and savings. If you take any relationship, there will be a causal relationship between the variables we are going to study. Third one is linear nature. So if the variables are plotted on a normal scale, the plotted points will form a line. Actually, in general thing, if we get a non-linear relationship, but for our computation, non-linear computation is very difficult to compute. So for Karl Pearson's coefficient of correlation, we are making that assumption that if we plot the values in a curve or in a graph, then we will get a normal curve, that they will form a line. That is the assumption, third assumption we are making. So that is the linear nature. So three assumptions, one is normality, second one is causal relationship, and third is linear nature. Now, if you see this method is the most widely used method for measuring correlation, Karl Pearson's coefficient of correlation. Then this is also known as Pearsonian coefficient of correlation, and it's denoted by the symbol small r. Now, what are the properties of coefficient of correlation? The value of r will always be between +1 to -1. If you're getting a value more than 1, then you can see that you have to recalculate because your answer is wrong. Always the value will be between +1 to -1. Now, the value of r cannot be greater than 1 in any case. So that I have already explained, value when you are checking, you have to see that value is always between +1 to -1. Then Pearsonian coefficient is independent of change of scale and origin of x and y variables. This is an important property. I am going to explain one module with two problems for explaining this concept alone. That is, see for a value, x values and y values. We can add certain values, we can subtract certain values, we can make addition, subtraction, anything. Then if you calculate the two sets of values, the first the given set and the second one is the converted set, then also the value of r will be same. So that is an important property. Pearsonian coefficient is independent of change of scale and origin of x and y variables. Now Pearsonian coefficient of correlation is the geometric mean of two regression coefficients. So that means r is equal to root of bxy into byx. So this will be useful when we are learning regression coefficient. If you know the regression coefficient values, we can get the correlation coefficient value. So this is an important property of correlation coefficient. Now, merits of Pearsonian coefficient of correlation. Most popular method of studying correlation is the Pearsonian coefficient of correlation. And this is the mathematical method. When we learn the problem, you will understand that. Then Pearsonian coefficient summarizes in one figure the degree and direction of change. That meaning, I told you the r value will be always between +1 to -1. That meaning you will get a value and you will get a sign, whether it's plus or minus. Plus sign meaning the variables are moving in the same direction. If one variable is increasing, the other variable is also increasing. If negative meaning if one variable is decreasing, the other variable is increasing, opposite. So we will get the direction and the amount of change. So this is an important property and it's a merit of Pearsonian coefficient of correlation. But there are limitations of Pearsonian coefficient of correlation. First one is Pearsonian coefficient always assumes linear relationship regardless of the fact that whether the assumption is correct or not. I told you in general we are getting a non-linear relationship. But what we are assuming that in the assumptions, 3 assumptions we assume that always we are assuming linear relationship between the variables. Next is often Pearsonian coefficient is misinterpreted. If you are making a wrong interpretation, then it will give a wrong interpretation for others, those who are using the value. Next is value of correlation coefficient is unduly affected by extreme items. If extreme values are there, compared to the other values, small values are there or higher values are there, the final answer can get affected. Next is Pearsonian coefficient computation takes more time in computing. You have to take the square root, you have to do calculations. If it's actual mean or assumed mean, it's taking time to compute. Then the computation is difficult for some. They will find it difficult as the computation is a lengthy procedure. Now, computation. So, the formula for computing R is equal to sigma xy divided by root of sigma x squared into sigma y squared. Now, we are taking actual mean. So, that meaning actual mean will be the x bar, that will be the capital X bar. When you are taking deviations, we are denoting it as the small x. That is why you can see in the equation all small letters sigma xy, sigma x squared and sigma y squared. So, take deviations of x series from the mean x series, that is the x bar. Then that is the small x. Then take deviations of these values, that is sigma x squared. Similarly, we have to repeat for y series, that is you have to calculate the mean, then take deviations from actual mean, then that value will be the small y. Then take the deviations of these values, that is sigma y squared. And finally, you have to multiply the deviations x and y, that is sigma xy. Then apply the equation. So, we are going to explain with one problem. So, calculate Karl Pearson's coefficient of correlation from the following. Values of x 6, 8, 9, 14, 17, 28, 24, 31 and 7. Values of y 10, 12, 15, again 15, 18, 25, 22, 26 and 28. As the first step, you know that we have to calculate the mean of x series and y series. These are individual observations. So, how you calculate? Sigma x divided by n, that is for x series. Similarly, for y series, sigma y by n. Sigma x meaning total of all the x values and n is the number of observations. So, if you see for mean of x series is 144 divided by 9, that is equal to 16. Mean of y series is 171 divided by 9, that is 19. Now, if you see the computation, x series is there, small x is capital X minus 16, that is the actual mean of the series. So, you will get the small x values. Minus signs are there and plus signs are there. Sign is important, you have to consider that. Then you have to take the deviations of x square values, that is 100, 64, 49, 4, 1, 144, 64, 225 and 81. The total also you have to take, that is 732. We are going to use this value in the equation. Similarly, y, the mean of y is 19. Now, we are taking deviations and your deviations, we are denoting it as the small y. That is, here also minus signs are there, plus signs are there. Then you have to take the deviations of y square values. That is 81, 49, 16, again 16, 1, 36, 9, 49 and 81. So, the total of y square is 338. Now, you have to take the you have to multiply small x and into small y. That is xy. That is 90, 56, 28, 8 minus 1, 72, 24, 105 minus 81. So, total is 301. Now, you have to substitute these values in the equation. So, you know that R is computed using the equation sigma xy divided by root of sigma x squared into sigma y square. That is equal to 301 divided by root of 732 into 338. So, that is plus 0.6051. Now, we have to interpret the value also. See, I told you, when we are getting the computed value, we are getting a plus and we are getting a figure. So, one value will tell us the direction and the amount of change. That is an important property of correlation coefficient. So, here plus sign meaning it's a positive correlation. That I told you, variables are moving in the same direction. If one variable is increasing, other variable is also increasing. If one variable is decreasing, other variable is also decreasing. Whereas if it was negative, if one variable is increasing, other variable will be decreasing, or vice versa. So here it is positive correlation. Now always you have to remember that when you are interpreting the value, we have to write that interpretation properly. So plus 0.5 or above, we will show it as moderately positive correlation. As the values increase, we will change our interpretations. If you are getting 0.9, then we will say that very high positive correlation. Like that, we have to interpret the values. 0.6051. So moderately high positive correlation. We are saying that as one variable is increasing, other variable is also increasing. Or if one variable is decreasing, other variable is also decreasing. So in correlation coefficient, writing the interpretation is important, and along with the answer, we expect the interpretation also. So this is what I want to explain with this module. Thank you.